Hello, students. In this lecture, we will study about systems described by differential equations. That means how we can be able to determine the output if the system is described, the input-output relationship of the system is described by linear constant coefficient ordinary differential equation. For example, if I have, for example, this circuit and the relation between the output yt and the input x of t can be related using differential equation. That means the output yt is, for example, the voltage across the capacitor is output yt, and the differential equation relating the input voltage and the output voltage is dy by dt plus ayt is equal to b times x of t. And b are constants, okay, which can be determined from the circuit, for example, from the resistor and the capacitor elements. In this case, for example, y of t is Vc of t, the voltage across the capacitor. X of t is Vs of t, the input voltage. And A is equal to B is equal to 1 over RC. So this is one example of differential equation for a circuit application for an electric circuit. Some other systems we have, for example, motion of vehicles across a surface where there is a friction and there is there are acceleration inputs, and some other control systems. Many other control systems can be described by differential equation, and the idea is to find the output given the input x of t. So when we are solving such kind of systems, we need to know what we call auxiliary conditions or initial initial conditions for the system. That means when the system is starting at t is equal to 0, what are the initial conditions? And we need to know the differential equation. And of course, we need to know the input, and we can find the output by following certain procedures that we will study. Now, in general, any nth order differential equation for linear time invariant system can be written using this. From k is equal to 0 until n ak, the k's derivative of y of t by dt k is equal to, from k0 to m bk, the k's derivative of x of t by dtk. Okay, this is a compact formula. When we expand this summation, we have a0 plus a1 dy by dt plus a2 the second derivative of y by dt plus plus plus, and the last one an, the nth derivative of y by dt n is equal to, on the right side, the same b0 plus b1 x of t plus b2 the second derivative, b1 is the first derivative of x of t plus b2 the second derivative of x of t until bm the mth derivative of x of t. Usually n is greater than or equal to m, and n is greater than 0. And as this kind of system, of course, it has memory if n is greater than 0. The initial conditions to solve is if the system starts at time t naught is y at t naught, and the derivative of y at t naught until the n minus 1 derivative of y at t naught. Of course, if the system starts initially, if it was when the system starts, if it was at rest, we assume the initial conditions is equal to 0. And the system stability depends, of course, on the coefficients of the AKs. For a first order system, for example, this is that differential equation. If I have a01 and if I have dy by dt and here minus a1 yt is equal to 0, this system has output a times e to the power of a1t. And if a1 is greater than 0, the system will be unstable because it is not absolutely integrable. And if a1 is less than 0, the system will be stable because the impulse response is absolutely integrable, or it's a decaying exponential function. Now, when we come to the solution of a system described by differential equation, we have two ways, okay, two ways to find the solution. The two alternative ways. The first alternative way is to find the homogeneous solution and the particular solution, and after that, the complete solution, which is the homogeneous plus the particular. The homogeneous solution means the solution of the differential equation without the input, which means if I go back here, the input is 0, means this equation, the left side is equal to 0. So the right side will be equal to 0. So the solution, when we solve this, will give us a homogeneous solution. The particular solution is a solution similar to the input, okay, because it is excited, the system is excited by a certain input. So the particular solution will have a form of the input. Then we combine the homogeneous solution and the particular solution, and we will get the complete solution. And there are some constants that we have to solve. Those constants can be found from the initial condition of the system, which we described before like this. For a first order system, for example, I will have only one initial condition. For a second order system, I will have two initial conditions. Y at t naught, if it starts at 0, y at 0, and the derivative of y by dt at 0. For a third order system, three initial conditions, and so on. This is one way, one alternative. The other alternative for the solution is finding the natural response and the forced response, and the total solution will be the sum of the natural response, the natural response plus the forced response. The natural response means the component of the output associated with the initial conditions, considering the initial conditions, and considering the homogeneous solution. That means we solve the homogeneous solution. Remember, the homogeneous solution is this is equal to 0. After that, the homogeneous solution will have a certain form where there are some constants. Those constants, we solve them from the initial conditions, from the given initial conditions. Okay, and we'll find the natural response. And the forced response means the homogeneous plus the particular, but with the initial condition is equal to 0. That means we assume when we have the forced response, we assume the system starts at rest. The initial condition is 0. So we forget all the previous initial conditions and we get the forced response. Then the complete solution will be the natural response plus the forced response. We'll have examples, more examples also in the next lecture, and you'll understand the difference between the two. Okay, so let's start with the homogeneous solution. The homogeneous solution is we solve, we say the input is equal to 0 and we solve it, and we have this. And the solution for this, you have to study it by your heart, this from k is equal to 1 until n ci e to the power of rit. So if the order of the differential equation is 1, I will have c1 e to the power of r1t. If the order is 2, I will have c1 e to the power of r1t plus c2 e to the power of r2t. I will have two roots r1 and r2. If the order is 3, I will have C1 e to the power of R1t plus C to the e to the power of R2t plus C3 e to the power of R3t. So how we get these Ri's? The Ri's can be found by solving the polynomial equation, or we call it the characteristic equation. The characteristic equation or the polynomial equation is summation from k is equal to 0 until n ak r power of k is equal to 0. So when we expand this, it means a0 plus a1r plus a2r square plus until n. A n r power of n is equal to 0. The s we can find them from the differential equation. Okay, we collect them from the differential equation. Then this equation will be a function of r. So it means solving a polynomial equation, which is a function of r. And then we find the roots of this equation. From that, we will determine the r's. For example, if it's second order, I will have a0 plus a1r plus a2r squared is equal to 0. And this equation is, as you know, the quadratic equation, and it will have two roots, r1 and r2. So the homogeneous will become C1 e to the power of R1t plus C2 e to the power of R2t. The particular solution will have the form of the input, as we said. If the input is unit step, it will be a unit step. It will have the unit step form. If the input is exponential function, it will have exponential form. And if the input is sinusoidal function, it will have it will be sinusoid form. Now, there is one thing also, if the roots are repeated. So if I have, for example, two roots which are repeated, then I will have C1 e to the power of R1t times t times e the power of R1t. So because there is no R2, R1 is equal to R2. So we need to modify the second by multiplying by t. If I have a root which is repeated p times, then the solution will consist of these exponential functions. That means. Now, if the roots are real, then we will have real exponential signal solution. If the roots are imaginary, we will have sinusoidal solution. If the roots are complex, we will have exponentially damped sinusoid solution. The particular solution should be independent of all the terms in the homogeneous solution. That means if I have a particular solution similar to the homogeneous, then again I need to modify it by multiplying by t like this. Okay. Now let's start with an example. Let's have a differential equation where we have dy by dt plus 2yt is equal to x of t. And we have the input x of t exponential function k times e to the power of 3t times ut, where k is a real number. Find the output yt. Okay, given the initial condition here is y at 0 is equal to 0, because usually if it's not given, then you assume it is 0. So y at 0 is 0. Because it's first order, I need one initial condition. Now, the solution for the homogeneous is the homogeneous will be yh of t d by dt yh of t to yh of t is equal to 0. A0 is 2, A1 is 1, N is 1. So we make it, okay, we compare it with the original equation with this equation. That means A0 is the derivative where there is no derivative, the coefficient of y where there is no derivative. A1 is the coefficient of y where there is first derivative. A2 is the coefficient of the second derivative of y. A3 is the coefficient of the third derivative of y. Okay, that's why. So from that relation here, A0 is the coefficient of y, which is 2. A1, the coefficient for the first derivative of y, which is equal to 1. N is 1, that means first order system. Then we solve this polynomial equation or characteristic equation from k0 to 1 a k r power of k is equal to 0, a0 r power of 0, a1 r is equal to 0, then r is equal to minus 2. Because it is first order, I will have one root, of course. Then the homogeneous will become C1 e to the power of minus 2t. Now, if the system, now this is a homogeneous solution. If we find the natural response, we will assume the initial condition is 0. We take the initial condition 0 and we solve for C1. But if we solve this using the first alternative, which is first the homogeneous, then the particular, we keep C1 here, and C1 later we will solve it from the complete solution, okay? From the complete solution, using the initial condition is equal to 0. Now the particular solution, because I have here exponential input, the particular solution will be the same, similar. So it will be Cp e to the power of 3t ut, or here I just use y e to the power of 3t, where y is a certain constant. Then we substitute in the original equation this yp, okay? But so if we substitute in the original equation here, I need the derivative of y particular, and the derivative of the particular solution is 3 times y e raised to 3t. That's the derivative of yt here. And then 2 times yt, 2 times of this is equal to x of t. Then we just have this 5 times y e raised to 3t is equal to k times e raised to 3t. And from here we can calculate y is equal to k over 5. This is the constant for the particular solution. So the complete solution now is C1 e raised to minus 2t plus k over 5 e raised to 3t for t greater than 0. Now, is it complete? Not complete. We need to solve C1. What is C1? Okay, C1 using the initial condition. The initial condition, for example, here we assume the initial condition is 0. If it is given another different constant, we use that constant. But for this example, the initial condition is 0. Then y at t is equal to 0. 0 means C1 plus k over 5 is equal to 0. And C1 is equal to minus k over 5. Then the finally we add the two. This will be the complete solution. Okay. So how we solve this? To summarize this, we solve it using the first alternative. Remember, the first alternative is to find the homogeneous solution, to find the particular solution, add the two, homogeneous solution plus particular solution, to get the complete, and solve the constants using the initial condition. That is the first way. Okay, that's what it. We solved the homogeneous, and we got the homogeneous solution, which is this one, C1 e raised to minus 2t. Okay, then we found the particular solution. We find y, and the particular is this, and we added the two, and we find the constant C1 from the initial condition. This is the first way, the first alternative. The other alternative is the second alternative, as I described before, is finding the natural response and the forced response, and add the two will give you the complete solution. The natural response, it is similar to the homogeneous, but we will solve the constant of the homogeneous by using the given initial conditions. If the initial condition is 0, we use that initial condition. If it's different from 0, we use that initial condition, and we solve for the constant of the homogeneous solution using the initial conditions. That will be the natural response. The forced response will be, okay, the homogeneous plus the particular, but assuming the initial condition of the system is 0. This will be the forced response, and we add the two. Okay, so we will have example for this also. Okay, so the natural response, as I said, is solving first the homogeneous solution this one, and it will have this form. And we solve for the R's from the polynomial equation. Okay, and we will find the constants from the initial condition. Okay, for the constants C1, C2, and so on. That means, okay, and then with the forced response, the forced response will have a particular solution and a natural response. The form of the natural response, the particular solution, and we find the constants of the natural response by assuming the initial condition is equal to 0. So, here is the procedures to find the forced response. Find the form of the natural response from the roots of the characteristic equation. Find the particular solution of the same form as the input but independent of all the terms in the natural response. Determine the coefficients in the natural response so that the forced response has 0 initial conditions. So the complete response is equal to the natural response considering the initial conditions plus the forced response with initial conditions set to 0. Okay? Or the complete response is the forced response with actual initial conditions instead of the 0 initial conditions. So let's solve this using the second alternative. First, we calculate the forced response, the natural response, and then the forced. This is an RL circuit, a series RL circuit. So this is an application of differential equation for electric circuit analysis. Here is a resistor, and let's say I have here a current flowing through this series circuit. This is L, and the output is the current flowing through the circuit. And let's call the current Y of t. Okay, I have an input voltage X of t. I have a resistor, I have inductor, and I have a current flowing in this series circuit, and I can take this as an output YT. You can take any output, for example, the output of the resistor, the output voltage of the inductor, and so on. This is up to you to decide. In this case, in this example, the current is the output Y of t. So this is a differential equation. R times the current, R times, if we use KVL, the input voltage X of t equals to the voltage across the resistor plus the voltage across the inductor. The voltage across the inductor is L di by dt, but the current is Y, so L dy by dt. The voltage across the resistor is R times I of t, which is R times Y of t. So this is the differential equation. As you see, it is first order, and n is equal to 1. A0 is the coefficient of y, r. A1 is the coefficient of dy by dt, L. B0, the coefficient of x of t is 1. Now we find the homogeneous solution by making it equal to 0. From this, we will find, by solving the polynomial equation, we'll find R1, it will have 1 root negative R over L. So YH of t is C1 e to the power of R1t, where R1 is negative R over L. Now, if the initial condition is given here, it's 2 ampere. Initially, the circuit has the current through the circuit is 2 ampere. So using this 2 ampere, I can solve for C1, and that will give me the natural response. Okay, so y at 0 is equal to 2, means C1 e to the power of 0 is equal to 2. So that means e power of 0 is 1, C1 will be 2. Therefore, the natural response will be y of t 2 times e to the power of r over lt ampere for t greater than 0. Now we found the natural response. The next one is the particular, the forced response. Now here the input is given cosine of t. Cosine of t, for cosine of t, the particular solution if I have cos omega naught t, the particular solution will be C1 plus cos omega naught t plus C2 sine omega naught t. This is the form of the particular solutions. It will have cosine and sine. C1 cos omega naught t plus C2 sine omega naught t. So we have to solve C1 and C2. How we solve? By inputting this particular solution here in the main equation. The main equation is R times Y, okay? L dy by dt is equal to xt. So we need the derivative of this first. What's the derivative of this one? The derivative of the first part is minus C1 omega naught sine omega naught t. The derivative of the second one is C2 omega naught cos omega naught t. Then put it here times L. And then R times Y of t, R times everything here. This is equal to X of t. Then we rearrange this. We group the cosine part. The cosine part is here, for example, R times C1. I have here one cosine and another cosine. I have here L omega naught C2. So I combine these two, and the cosine part should be this cosine part. So that means the coefficient RC1 plus L omega naught C2 is equal to 1. The sine part, I group the sine part R times C2 minus L omega naught C1. The sine part, I don't have sine here, should be 0. So I have two equations with two unknowns. The unknowns are C1 and C2. Omega naught R, L, they are given from the circuit itself, okay? So by solving these two equations with two unknowns, we know this is simultaneous equation. We'll have C1 is this one and C2 will be this one. Then finally the particular solution will have this, okay? The particular solution will be this. So the forced response will be the homogeneous solution, which is this one, plus the particular solution, plus the particular, which is this. Now let's substitute R and L. Omega naught is 1 given. The resistance is 1 ohm. The inductor is 1 Henry. Then substitute everything. Then the forced response will be this. C1 e to the power of minus t half cos t half sin t. Now, to find the complete forced response, we assume the initial condition is 0. So with the initial condition 0, then y at forced is equal to 0, t is equal to 0, 0, c e to the power of 0 plus half cos 0 plus half sin 0 is equal to 0. Then c will be negative half. So this way we found the forced response. Remember the complete solution. Complete is the natural response, which we found it 2 times e to the power of r over lt, plus the forced response, okay, with the forced response, which is this one, okay, and the natural response, this one. Add these two, we'll have the complete solution, okay. So this is the second alternative to find the solution. So to summarize how we find the solution, by first getting the homogeneous solution and then the particular solution and solving the constants using the initial conditions. This is alternative 1. Alternative 2, find the natural response and the forced response, and the complete solution is equal to the natural response plus the forced response. Here is the graph of the natural response here. Here is the graph of the forced, and the total response is this. Okay, so that's all the first part of the differential equation. We will have more examples in the next lecture class to have more understanding about solving systems described by differential equation. And thank you for listening to this lecture class.